Hey guys, let's go ahead and read about our telescopes. Telescopes are designed to collect a certain type of electromagnetic waves. Some detect visible light, and others detect radio waves and microwaves. Optical telescopes. Whoops. Like your eyes, optical telescopes gather only visible light. There are two kinds of optical telescopes: refracting and reflecting telescopes. Both are shown on the right. So it has everything to do with like the shape of the lens and how it's coming into your eyepiece. Refracting telescope. Have you ever used a magnifying lens? You might have noticed that the lens was curved and thick in the middle. This is a convex lens. So I see a vocab word, so I'm going to stop and highlight that. A refracting telescope uses a convex lens to concentrate light from a distant object. The objective lens in a refracting telescope is the lens closest to the object you are looking at. The light goes through the objective lens and refracts, forming a small, bright object. The eyepiece is the second lens that magnifies the image. It's not necessary that we know like the different lenses and stuff in with this telescope, but just that there are two different types of telescopes. Okay, okie dokie on that. Okay, so reflecting telescope. Most large telescopes use a curved mirror instead of a curved lens. A reflecting telescope uses a curved mirror to concentrate light from a distant object. It reflects light from a primary mirror to a secondary mirror. The secondary mirror is tilted to let you see the image. Larger primary mirrors usually produce clearer image than smaller mirrors. The very large reflecting telescopes have many small mirrors linked together to make a primary mirror. For example, each 10-meter primary mirror in the twin Keck telescopes on Hawaii's Mauna Kea consists of 36 smaller mirrors. Okay, so I'm going to stop here and I'm going to look at our notebook. I'm going to see what is it that we need to do. What can we do so far with what we read? Okay, so I'm going to start out with this graphic organizer. So we have Earth-based telescopes. So we learned in this first section, we learned about optical. They gather visible light. Okay, so we know that there are two types of optical, and that is refracting and reflecting. Okay, all right, so let's take a look at that to support that. So we know that optical only gather visible light, and we have refracting and reflecting. Okay, so refracting, it uses a convex lens to concentrate light from a distant object. And reflecting uses a curved mirror to concentrate light from a distant object. So they both concentrate light from a distant object. It just depends on what type of lens or mirror. One has a lens, one has a mirror, okay? So that is the difference between a refracting and a reflecting telescope. Okay, so let's go back to our reading essential. And so we knew the refracting uses a convex lens and a reflecting uses a curved mirror. Okay, so we have that supported with our science notebook. Okay, so let's go on to the next. Our next here is going to be a radio telescope. So an optical telescope collects visible light waves, but a radio wave collects radio waves and some microwaves using an antenna that looks like a TV satellite dish. These waves have long wavelengths and carry little energy. So radio antennae must be large to collect them. Radio telescopes are often built together and used as if they were one telescope. Computers convert radio data into images. Okay, so let's take a look at our science notebook. And let's look here now on the right-hand side. So we had optical, that gathered visible light. And now we have, let's go ahead and change that color. We have radio, that collects radio waves. Shocker, huh? Radio waves and some microwave. So that uses large radio antenna often in arrays. All right, so we know an array is going to be something like this, okay, or some type of configuration, some type of pattern. And so they are going to collect radio waves. Okay. So I can't do any more without reading more. So let's go back to our reading essential. Distortion and interference. Moisture in Earth's atmosphere can absorb and distort radio waves. That's important to know. Our atmosphere is going to get in the way of these radio waves. So most radio telescopes are located in deserts, far away from radio stations that emit radio waves. So we want to get as far away as we can and in a dry area because moisture can absorb and distort these radio waves. We also want to get away from other radio stations that might be giving off radio waves. We don't want to be collecting those. We want ones that are coming through the atmosphere. Okay, so we're going to locate them in deserts. And so most radio telescopes are located in deserts far from radio stations that emit radio waves. These radio waves can interfere with radio waves from space. Water vapor and other gases in Earth's atmosphere also distort visible light. Stars seem to twinkle because gases in the atmosphere move, refracting the light. Let's go ahead and highlight that. That's kind of cool. So it's not actually that the stars are twinkling out there, but the gases in the atmosphere move a little bit and it's going to refract that light. So it's going to give that appearance that the stars are twinkling. This causes the location of the star's image to change slightly. At high elevations, Earth's atmosphere is thin. This produces less distortion than at low elevations. So most optical telescopes are built on mountains. New technology called adaptive optics reduces the effects of atmospheric distortion even more. Okay, so let's take a look at what we can do on our science notebook, okay? All right. So the placement of most Earth-based telescopes. So let's come on over here. to optical. Which one are we going to put up on a mountain is going to be an optical one. That's the one that does visible light. Okay, so the reason why they're going to do that is because we have thin atmosphere produces less distortion. We want things as clear as possible. Less distortion of light. Okay, so we're going to put it right up there on the top of the mountain because the atmosphere is thin. That's going to produce less distortion. So we have our other type of telescope, and that's going to be a radio. And where we're going to put that, we're going to put that in the desert because of the dry environment. Produces less distortion. From atmospheric moisture. Okay, so let's stop and let's take a look at that. We're going to put an optical, which is going to be collecting the visible light waves high up on a mountain because that thin atmosphere produces less distortion of the light. We're going to put a radio, which is going to be collecting radio and microwaves, some microwaves. We're going to put that out in the desert because we need a dry environment, and that's where a desert is, and it's going to produce less distortion from the atmospheric moisture. So the moisture would be providing interference and distortion with that radio signal. Okay? All right, so make sure you have all of that done. And now if we look here, we're ready for our space telescopes. Okay, so let's go to our reading essential. Okay, and if we look at this graph here, wavelengths from space, all right, wavelengths from space. All right, we see the visible light gets right through that really easily. Radio waves also, microwaves, some infrared doesn't get all the way in there, okay? Ultraviolet, X-ray, gamma. So if we're going to have a Earth-based telescope, we're not going to be able to have one that collects infrared or UV or X-ray or gamma because they don't reach the surface of the Earth. That's because most of that is absorbed by the Earth's atmosphere. But the radio waves and the microwaves and the visible light waves can get all the way through Earth's atmosphere. So we can have Earth-based telescopes that collect those waves. We're not going to put an Earth-based telescope that is trying to collect X-rays or UV waves because it's not going to reach the Earth, okay, because here's the Earth, okay? All right, so we're going to put way up here. Here is our mountain, and here's our desert, okay? All right, space-based telescopes. Why would astronomers want to put a telescope in space? The reason is Earth's atmosphere. As the figure above shows, visible light, radio waves, and other microwaves reach Earth's surface. Other types of electromagnetic waves do not. Earth's atmosphere absorbs some of the electromagnetic radiation. All right, so let's go ahead and highlight that. Visible light, radio, and some microwave reach Earth's surface. Others do not, and you can see that. Okay, and that is because Earth's atmosphere absorbs some of the EM radiation. Telescopes on Earth can can collect only the EM waves that are not absorbed by the Earth's atmosphere. All right, so that we talked about that already. So radio, micro, and visible are the only ones that are going to reach the Earth's surface. So those are the only types of telescopes that can be put on Earth's surface. So if we want to be collecting these other waves, we got to get outside of our atmosphere. So you have to have a space-based telescope. Okay, but telescopes in space can collect energy at all wavelengths, including those that Earth's atmosphere would absorb, such as infrared, most UV, and X-ray. Okay? All right. I want to take a look, and I believe that we can do a little bit on our notebook here. So, differentiate the collection of electromagnetic radiation. All right. Let's make a stronger color. Okay, these can be collected by telescopes on Earth's surface. So what waves can? Visible light. What else? Radio. What else? Some microwaves. Okay, which one cannot? Would be most infrared. Oop, I did not do a good job of spelling that. Sorry, guys. Okay, infrared, most UV, X-rays, also gamma. And that is because these are all absorbed by Earth's atmosphere. Oop, sorry about that, guys. Did not give myself enough space there. Alrighty, so the ones that can reach Earth are going to be able to be collected by Earth-based telescopes, like optical. This is our optical. And this is our radio. But these guys over here, they cannot be collected by telescopes on Earth's surface because those waves do not make it. Whoops, that was the wrong resource there. Okay, so make sure that you have this section filled out in your science notebook. Okay, you can stop the video at any point if you need to. All right, so we're going to be looking at space telescopes here. So let's continue reading. Optical space telescopes. So let's go ahead and highlight that. Optical telescopes collect visible light on Earth's surface, but they work better in space. Let's go ahead and highlight that. This is because of Earth's atmosphere. As you read earlier, gases in the atmosphere can absorb some wavelengths, but in space there are no atmospheric gases. The sky is darker and there is no weather. The first optical space telescope, called the Hubble Space Telescope, was launched in 1990. All right. The Hubble is a reflecting telescope that orbits Earth. Its primary mirror is 2.4 meters in diameter. At first, images from the Hubble were blurred because of a flaw in the mirror. In 1993, astronauts repaired the telescope. Since then, the Hubble telescope has sent to Earth many spectacular images of faraway objects. And we will go ahead and have some videos. I have some video clips up with images from the Hubble. We'll do that a little bit later, okay? Not today, another day. All right. Using other wavelengths. The Hubble telescope is the only space telescope that collects visible light. That's important. Dozens of other space telescopes operated by many different countries gather UV ultraviolet, X-ray, gamma, and infrared. So let's change that. So dozens of other space telescopes operated by many different countries gather UV, X-ray, gamma, and infrared. Now, those are not going to be able to be on Earth-based, right? Because they can't make it through the atmosphere. Each type of telescope can point at the same region of the sky and produce a different image. And that's because, remember, these telescopes, they're going to be picking up a certain type of EM wave. So what's being emitted by stars are different, primarily, we learned about that yesterday, that a star will give off all these EM waves, but primarily one. Like our star primarily gives off visible light, right? Okay, so each type of telescope can point at the same region of sky and produce a different image. An image of a star can be made by combining optical, X-ray, and infrared data. Different colors in the images represent the different wavelengths of the material in the star. So we have a Spitzer. Let's go ahead and highlight that. Spitzer Space Telescope. Young stars and planets hidden by dust and gas cannot be viewed in visible light. But infrared wavelengths can go through the dust and show what is beyond it. Astronomers can also use infrared to observe objects that are too old or too cold to emit visible light. In 2003, the Spitzer Space Telescope was launched to collect infrared waves as it orbits the sun. Let's go ahead and highlight that. All right, so the Spitzer is going to pick up infrared wavelengths. Okay. All right, we got ourselves another type of telescope, the James Webb Telescope. A larger space telescope scheduled for launch in 2013, it's been delayed, is also designed to collect infrared radiation as it orbits the sun. This James Webb Space Telescope will have a mirror with an area 50 times larger than Spitzer's mirror and 7 times larger than Hubble's mirror. Astronomers plan to use the telescope to detect galaxies that formed early in the history of the universe. So the purpose of that is to collect galaxies, detect galaxies. Okay? All right. So let's go into our notebook here. And we have just these last two sections to do. So we have our space. We're contrasting the quality of optical telescopes that are Earth-based with those that are in space. So in space, it is going to be clearer because we don't have that atmosphere getting in the way. We have Earth here. So we have space-based and Earth-based. The image is going to be clearer out in space, but in Earth it can be distorted. So what's the explanation for that? And that is because the sky is darker and there is no weather. Because, if we're trying to look with an Earth-based telescope on a cloudy day, you're not going to be able to see anything. But you get yourself outside of our atmosphere, we're not going to have to contend with weather and clouds and those types of things. The sky is darker and there is no weather because there are no atmospheric gases. Okay, so nothing to distort. Okay. All right, so that's all going to go in that section. I apologize that I took up so much of that space there. That's okay. Okay, so Let's see, can I do that? Scoot that up? That didn't work for me very well, did it? All right. I need to just leave that alone. Okay, the sky is darker and there is no, let's just leave that alone. Okay. So the sky is darker and there is no weather because there are no atmospheric gases. Okay, so what about Earth? All right, so on Earth, let's go ahead and change that color. The explanation why Earth it just distorts, why the space are clear, is because of our atmosphere again. Okay, so the gases of Earth's atmosphere distort image. And because we have weather and we have clouds, okay? So this coming over here, so this is why stars twinkle. And that is because the light reflects off the gases in our atmosphere. The stars are not twinkling themselves. It's just the light is being distorted as it's moving through our atmosphere. Okay? All right. So stop this video and get that filled out if you need to. Okay. So then we're going to, so this section here went with the different types of telescopes. We had our Hubble, we had our Spitzer, and we had our James Webb. There's been a lot of delays in with that James Webb telescope, but the Spitzer and the Hubble are in use. Okay, so I can't split screen this because it's just too small, but you probably have the ability to split screen a little bit easier than me. Okay, so the wavelength observed with a Hubble is visible light. It is an optical telescope. Okay. The launch date was 1990. It orbits Earth. Okay. All right. So we're going to leave the size here in just a moment. All right, so we could go back and we could look at that. Is the only space that collects visible light, and it is orbiting. It is orbiting Earth. Its primary mirror is 2.4 meters in diameter. So we are able to come down now here, and it's 2.4 meters. Okay. Now, the Spitzer, what is it going to collect? It's going to collect infrared waves. Its launch date was 2003, and it orbits the sun. Okay. So we can get all of that information from here. Infrared, it's 2003, and it orbits the sun. Okay, 2003. Okay, infrared. Now we have our James Webb. It also is going to orbit the sun. It's going to collect infrared. Okay. All right. Here we go. Let's change this color. And it's going to also collect infrared. it was scheduled for 2013 and then it was scheduled for 2018. All right, and it orbits the sun. Okay, so we're going to have to do a little math here. And to determine, because we have 7 times Hubble, we know the Hubble. Okay, we know the Hubble is 2.4. So we can go 2.4 times 7. Be 8, 28, 14, 16. Okay, so the Hubble, the Spitzer is going to be 16. That's the James Webb. 16.8 meters is the size of the mirror. All right, so that was the James Webb. So we have to use this number, the 16.8, to figure out what the Spitzer is. Okay, it's 1/50th of James Webb. All right, which was 16.8. All right, so that's a proportion. And so you cross multiply and then divide, and you come up with 0.34 meters. Okay, so that was kind of tough. You have to kind of work backwards with that. So let's get this. Make sure you have all of that in. Okay. All right, you guys have that? Okay. So this last question, synthesize it. Explain how scientists conclude the ages and distances of stars by observing their EM energy. Okay, so this one, I'm just going to read through, and we can write down this answer a little bit later when we go over it in class. But all EM waves travel at the speed of light, which is 300,000 kilometers per second. So astronomers can use that information to determine the amount of time light has been traveling from the star and the star's distance from Earth. Stars also cool as they get older, and looking at the type of radiation emitted will help reveal its temperature range. Okay, so we remember how we talked in class how I don't really know because I am not an astronomer or astrophysicist, but they are collecting all of this data from all of these telescopes and figuring out how long a star has been traveling based on the temperature, based on the EM wave that's being collected by that particular telescope, which is why you have to have all these different types of telescopes out in space to be able to collect all these different types of EM waves, right? Okay, so that wraps up this lesson. So go back and look at any of these that you need to complete. Do not worry about this at this point. Filling that in, we'll talk about that in class. Okay, guys? All right, have a good day.